Hello, we are first year students of Vishwakarma Institute of Technology. This is group 8 of class M, and today's topic for us is going to be restoring division algorithm.
Now we will be performing restoring algorithm for unsigned integer. Restoring term is due to fact that value of register A is restored after each iteration. Here, register Q contains quotient and register A contains remainder. Here, n bit divided is loaded to Q and divisor is loaded into M. Value of register is initially kept 0 and this is the register whose value is restored during iteration due to which it is named restoring. Let's pick the step involved. Step 1. First, the registers are initialized with corresponding values. Q equals to dividend, M equals to divisor, A equals to 0, and N equals to number of bits in dividend. Step 2. Then the content of register A and Q is shifted left as if they are in a single unit. Step 3. Then the content of register M is subtracted from A and result is stored in A. Step 4. Then the most significant bit of the A is checked if it is 0. The least significant bit of Q is set to 1. Otherwise, if it is 1, the least significant bit of Q is set to 0. And value of register A is restored. That is the value of A before the subtraction with M. Step 5. The value of counter n is decremented. Step 6. The value of n becomes 0. We get out of the loop. Otherwise, we repeat from step 2. Step 7. Finally, the register Q contains the quotient and a count contain remember.
So now let's move towards an example for better understanding of restoring division algorithm. So here we have taken an example of 11 by 4. Here, so according to the first step, the accumulator is set to 0 and the dividend 11 is stored in the register Q and the divisor, that is 4, is stored in the register M. So the dividend 11 in binary notation is in 4 bit, that is 1011. So the count is set to 4. Now moving towards the next step, we will shift the contents in accumulator and the register Q towards left. After this, we will add the 2's complement of 4, that is 11100 in the accumulator. After addition, we will check the most significant bit in accumulator. Here in the accumulator, the most significant bit is 1. So we will add 0 in the Q0th position. And now we will restore the accumulator by adding M. And here our first cycle gets completed and the counter is set to 3. In the next cycle, we will repeat the same process. We will shift the contents in the accumulator and the register Q towards the left and add the 2's complement of M, that is 11100. After addition, we will check the most significant bit in accumulator. Here the most significant bit is again 1 and we will add 0 in the Q0th position. Now restore the algorithm by adding M in the accumulator, and this is our end of the cycle and the counter is set to 2. Now again in the third cycle we will repeat the same process by shifting the contents of accumulator and the register Q towards left and adding the 2's complement of M in the accumulator and check the most significant bit in the accumulator. Here the most significant bit in the accumulator is 0. Now we will add 1 in the Q0th position. Here is the end of the cycle third and the counter is set to 1 because we don't need to restore the accumulator by adding M because the most significant bit here is 0. In last cycle, that is fourth cycle, we will repeat the same process again by shifting the contents of accumulator and register Q towards left and adding the 2's complement of M. After addition, we will check the most significant bit in the accumulator. Here the most significant bit is 1, so we will add 0 in the Q0th position. This is the end of the fourth cycle and the counter is set to 0. This is the end of the loop and the contents in the accumulator give us the remainder and the contents in the register Q give us the quotient. Here the quotient is 0010 and the remainder is 00011.
Moving toward another example to clarify more, taking an example of 13 by 4, here first we have to initialize the value to make it easier. A is initialized to 0, 0, 0, 0, Q which stores the dividend is taken as 13 and M which is 4 in its binary representation is shown as 0, 0, 1, 0, 0. Performing left shift operation on A and Q and then subtracting the contents of A and M. If A is greater than 0, that is most significant bit is 1, then Q0 will be set as 0. Now restoring A by adding it with M. Here the previous content is restored, decreasing the counter and again performing the left shift operation on A and Q, adding A with M's complement, that is
Now
2's complement
further,
of M,
as we have
and
discussed,
checking
we will
if
perform
A
a
is
shift
greater than
operation on A and
0
Q.
or not.
After that,
If A is
subtracting M
negative,
from
then
A
set
as per the
Q0 to 0
flowchart
and
that we
restore
have discussed
A
earlier,
by
the
adding
value of
M.
MSB here is 0. Now we will perform the operation. First, decreasing the counter and then adding A with M's complement. After A and M are added, we got a final result. That is A equals to 00001, which is our remainder, and Q equals to 0011, which is our quotient. From this, the value of the remainder equals to 1 and the value of the quotient is 3. By performing 13 by 4 operation, by restoring algorithm method for unsigned integer, we get our quotient as 3 and remainder as 1. Now, this is the end of our video. And we hope you understood the method to solve division algorithm for unsigned integer. Hope you like the video, and if you find it informative, please like, share and subscribe. Thank you.